In this lesson, we will discuss continuity of a function. Recall earlier when we were evaluating limits, for certain nice functions like polynomials and rational functions, to evaluate the limit of a function at a point, we could use direct substitution. The reason we could use direct substitution is because those functions were continuous at the limiting value of x. So we're going to discuss what does it mean for a function to be continuous. Consider the following graph of the function f. Anytime the function has a hole or a break in the graph, the function is not continuous. So in this example, we see that there's problems with this function at the point 1, at the point 2, and there seems to be a little hole at the endpoint 4. So whenever there is a break in the graph, this function is not continuous. But all the other places, like between 0 and 1, the graph is continuous. One way to think of it is if you can draw the graph of a function without picking up your pencil, then the function is continuous. So this is how you should think about continuity. A function is continuous if it has no holes or breaks in its graph. Let's be more precise when we talk about continuity. We're going to define continuous at a point using limits. We say a function f is continuous at a number a if the limit of f of x as x approaches a equals f of a. If you notice, this looks like what we did when we did direct substitution for certain types of special functions like polynomials. We just plugged in a into the function to evaluate it. So direct substitution is a consequence of a function being continuous at that point. So there are certain things that this definition implies. Intuitively, remember that a function is continuous at a point a if there are no holes and there are no breaks in the graph at the number a. But this definition implies three things. It implies that f of a is defined, that a has to be in the domain of the function. Further, it implies that the limit of f of x as x approaches a exists, and it also implies that the limit and the function's value at a are the same. So graphically, what's going on is that the function has no holes or breaks in the graph at a. So going back to this previous example, we see that the function is continuous between 0 and 1. The function is continuous between 1 and 2. The function is continuous between 2 and 4. But also we have some starting and stopping points. Whenever we have an open circle in the graph, it implies that there's no point there. If it's a closed dot, that means there is a point there. So for example, look at the graph at x equals 1. So can we say that the function is continuous at x equals 1? No, we can't. So the function is not continuous because you'd have to pick up your pencil to continue drawing the graph at x equals 1. But we can also talk about continuous from the left and continuous from the right. So notice that at x equals 1, the point on the graph is at height 1. And if I'm drawing the graph, if I'm following the graph for x values of x between 2 and 1, notice that the graph is continuous. I can draw a continuous line and put a dot at x equals 1 from the right. So we would say that the function is continuous from the right at 1. Since there's an open circle at x equals 1 on the left side, we would say the function is not continuous from the left at 1. Similarly, look at x equals 0. Since there's a closed circle at x equals 0, if you follow the function along the function from right to left, we see that the function is continuous from the right at 0. So this leads to the following definitions. First, if a function f is not continuous at a point A, we say that f is discontinuous at A. Or we can say that f has a discontinuity at A. A function f is continuous from the right at a number A if the right-hand limit of f of x as x approaches A equals f of A. So a function that's continuous from the right would have a closed circle, and then the closed circle would be connected to the graph to the right. So similarly, a function f is continuous from the left at a number A if the left-hand limit of f of x as x approaches A equals f of A. So if you had a graph that was continuous, like a continuous line, and then a closed circle as a stopping point, then that would be continuous from the left. So for this function, f has discontinuities at x equals 1, x equals 2, and x equals 4. We could also say that f is continuous from the right at x equals 0 and continuous from the right at x equals 1. Because if you approach x equals 0 from the right-hand limit of f agrees with the function's value. So there's a closed circle at x equals 0, and the function from the right approaches that closed circle. And at x equals 1, the same thing. There's a closed circle at x equals 1, and then the function to the right approaches and connects to that closed circle. Now let's talk about different types of discontinuities. Look at the graph of this function. This is the graph of sine of theta over theta. This function has a problem at theta equals 0. All of our trig functions are defined in radians. So this function, there's a problem when the denominator is 0. And if you see the graph of this function, there's a little hole at theta equals 0. So we could get rid of this discontinuity. We could remove this discontinuity by defining this function to equal 1 when theta equals 0. So you could kind of just fill in the hole there, and you would have a nice connected graph with no holes and no breaks. So we call this a removable discontinuity. So if the limit at a point exists, but there's a hole, then this is called removable. Now let's talk about a jump discontinuity. For this type of discontinuity, you cannot simply remove the discontinuity by adding one little point to the graph. In this case, the graph has a jump discontinuity at x equals 2 because the left-hand limit and the right-hand limit do not agree at x equals 2. So we call this a jump discontinuity. An infinite discontinuity occurs when a graph has a vertical asymptote. So this graph of y equals 1 over x has an infinite discontinuity at x equals 0. The last type of discontinuity is called an oscillating discontinuity. Recall when we were talking about limits that the graph of sine of 1 over x does not have a limit as x approaches 0 because the graph does not approach one single number as x gets closer and closer to 0 from either side. So since the limit as x approaches 0 of sine of 1 over x does not exist, the function cannot be continuous at this point either.